Okay. Good day, students. Welcome to GT 272 class. So today we are going to focus on lecture note 6 titled Mechanical Properties of Materials. You will recall that in the last video I posted, we concluded on the lecture 5, which is the imperfection in solids. So today we are going to look at mechanical properties of materials. Hopefully I should be able to round up this lecture also in this particular video. So welcome to another online class for GT272, that is engineering materials. So today, as I said, we are going to look at mechanical properties of materials. Now, this is a very important aspect of this course in trying to understand engineering materials. So we have spoke about response of materials to different stimulus in one of our earlier lectures. So today, basically, we are going to focus on one of those stimulus that we have spoken about, which is a mechanical load. So if you apply a mechanical load to a material, which is usually the case during the application of materials for most engineering application, you will observe that the material will have to respond to that imposed mechanical load. Now, the response of that material to the mechanical load is what determines the usability of the material for the particular engineering material. So if you want to use a material for an engineering application, you need to ascertain carefully that the material is designed specifically to satisfy that purpose. So one of the consideration is to look at the ability of the material to withstand the applied load, and that will be determined by understanding what the mechanical property of the material would be with respect to the load that is imposed on it. So the very first question one will want to ask is that why is there need for us to understand the mechanical properties of a material? So what it means is what this means generally is that if you want to design a material for an engineering application and you understand that one of the stimulus that will be imposed on the material during operation is mechanical load, that is force. When I say mechanical load, I'm referring to a force application. So if you understand that, then in your design of that material, you want a situation whereby the material is able to withstand the applied load without failure or fracture. So usually the essence of having a material being applicable for a particular operation is that you don't want it to fail. So once a material is able to perform the intended once a material is functioning as intended, then it means it has not failed. But once a material cannot perform the intended application, then it is said to have failed. So failure is what you want to avoid in an engineering practice. So in order to avoid that failure, one of the things to consider is to ensure that whatever material that you are using for that engineering application can withstand the applied load. So you must understand the load, you must understand the mode of application of that load, and lastly, you must understand whether the material can withstand that load or not. So if a material is able to withstand the load, then it means you say the material is able to sustain that particular, is able to function as you want. So how do you now understand when a material is able to withstand a particular load or not? So this is where you need to understand the mechanical properties of a material. So what it means is there are certain properties of the material that you need to understand, you need to know. Now, your knowledge of that material is what your knowledge of those properties is what we guide in the design of the material so that it will be able to withstand any the load in question that you expect it to bear during application. So let's take some examples on application of load on a material during in some of our regular day-to-day engineering practices. So you have some examples on this slide. So we have a material that is used in building bridges. So if you look at bridge, for instance, You see, it carries a lot of load. It is supposed to sustain whatever load that is moving on it. So you see, the materials that you are going to use in the design of this bridge must be the ones that can withstand the enormous load that will be moving on this particular bridge. So if you look at our houses, if you look at our automobile industries, if you look at building of skyscrapers, you need materials to carry out all of these structural designs. So basically, the material component is one that must be selected such that it is able to withstand the load that will be imposed on it during operation. So once you are able to do that, it means that the structure will stand the test of time, and then it will perform the intended function that you have set for it. So basically, one needs to understand the load, one needs to understand the mode of application of the load, and then one needs to understand the ability of the material to withstand the load. And this will be defined by the understanding of the mechanical properties of this material. So we're going to try to understand some of these properties, how you can measure these properties, and how the understanding of these properties can help in the design of a material that will not fail during operation. So what we're going to look at, we're going to focus on some basic principles. This is just an introductory class to understanding engineering materials. We're not going to be going so deep, just to understand some basic concepts of mechanical properties of material. So we're going to focus basically on understanding the stress and strain, the plastic behavior of a material when a load is applied, elastic behavior, and then some mechanical properties like strength, ductility, resistance, resilience, toughness, hardness, and how all of this can be measured. So I'm also going to, if you know these properties now, how does it guide you in designing a material that is suitable for an application, putting into consideration some design factor that will allow for the material not to fail during operation. So this is what we are going to focus on in this particular lecture. So let's start with stress and strain. So basically, in understanding the mechanical properties of a material, we are trying to understand the response of a material to an applied mechanical load. So usually when you apply mechanical load to a material in whichever form that it may be, the material will definitely respond. And the response of this material will usually come in terms of deformation generally. So upon application of a load to a material, there is going to be a response, and that response will come in form of a load. So what you have from the onset is a load deformation situation. So the applied force will cause a deformation of the material. So the question is, what is now the essence of stress and strain when ordinarily what you have from the beginning is force and the consequential deformation that results from its application. So basically, the stress and strain are quantities that allow us to be able to understand the effect of the applied load and the consequential effect of the deformation resulting from the applied load. So that is why the stress and strain becomes very important. So in understanding the behavior of a material as it responds to a mechanical load, you will have to start by understanding the relationship between the applied load and the deformation, and then the quantities are well defined and gives you a better understanding or a description of the effect of that applied load is stress, and then the consequential deformation that is resulting from the applied load is strain. So therefore, it is important to understand stress and strain. So these two are quantities that will allow us quantify what the effect of the applied load is, and the resulting deformation from the application of that load can also be quantified by understanding the strain. So to start with, stress is the pressure you apply on the material per unit area. So pressure due to applied load in simple statement defines what stress is. So mathematically, it is the ratio of the applied force per unit area, per the area of which the force is applied. So what it means is, if you apply a force on a material, so if you try to mathematically find if you want to mathematically find the stress, is to understand what the magnitude of the applied force is, If you divide by the original area upon which the force is applied, you will get a quantity that is called stress. Now, the strain now is the response to the applied load, which will come in form of a deformation. So that physical deformation that you get in the case of whether the material is being elongated or the length is being reduced is what defines the strain. So we're going to look at in detail what these two means as we go along. So when you apply when you apply load to a material, if looking at this slide, you will see four different figures, and what they are trying to do is an illustration of how tensile load can produce elongation, which is dependent on the type of loading that you are subjecting the material to. So basically, we have, you can load either in tension, you can load in compression, you can load in shear, and you can load in torsion. So four of them: tensional loading, compressive loading, shear loading, and all of this is going to result to some form of stress and strain. So if you want to measure the stress resulting from a tensional loading, you have a tensile stress or a tensile strength. If you want to get the compressive strength, it means you have to put the material through a compressive loading. For shear strength, shear strain, you need to put material through. So what do all of this mean? So what it means is that what defines the type of loading and the kind of stress or strain that you get at the end of the day is the direction of the applied load in relation to the direction of the normal of the surface upon which the force is applied. So for tension and compression, usually the force is perpendicular to the surface. So if you take a look at this, my laser pointer from figure A under tension. So you see the surface. This is the surface upon which the load is applied, and then the direction of the force is going perpendicular to that surface. So you will see that the force application is perpendicular to the surface, so you have a tensional loading. For compression loading, you have a similar situation. The applied force is also perpendicular to the surface. However, there is a difference between these two in terms of the direction of the applied force. So a tensional load will cause an elongation of the specimen, while a compressive load based on the direction of the two applied forces will cause a reduction in the length of the specimen. So what you can now conclude here is that it's all about they are in opposite directions. So while the tensional load will cause elongation, the compression will cause a reduction in the length of the material. So but these two, as you can see, have the forces applied perpendicular to the surface area upon which you are applying the load. So you have what is called, in this case, a normal stress, which is in form of a tensional and compressive loading. So if you come to the third one, which is a shear. So what you have with shear is a situation whereby the direction of the force is parallel to the surface upon which the load is being applied. So if you look at this colored surface and then look at the direction of the force that is being applied, so what you have is a form of a shear. So you see the deformation is such that the original structure is with the dotted line, while the resulting structure is with the thick line. So you can see the kind of deformation that you have as a result of that kind of loading. So this condition is what you call shear loading. And then for torsional loading, this is more of a twist. So this is like you're applying a load through a form of circular load that will cause like a twist. So now you see all of these loading conditions are applicable differently in different engineering applications. So say for instance, if you look at the load that you exert on your shaft, for instance, is you have more of a torsional load there because of the circular nature of the shaft and the mode of operation. So you will see that in that case you have to understand the torsion that will occur as a result of the circular load. So all of this is very important before you want to study the properties. So some simple common state of stress. So if you take this is an example of a sky lift. So if you look at the cable in a sky lift, this cable here is what is brought out here for you. So you can see that during the course of operation of the sky lift, you see there is a force application on the cable. Now that force application on the cable is going to exert a load on this cable, and then that load definitely is going to go through some stress. Now the stress on this cable can be obtained by simply dividing the magnitude of the force, which is the load on this cable, by the original cross-sectional area of the cable. It has to be the original cross-sectional area of the cable. So by doing so, you will understand the stress that is imposed on this cable. Now you want to understand that during the operation of this lift, you don't want this cable to fail. So what it means is the only way you can avoid a failure, one of the ways to avoid the failure of this particular a cable, is to ensure that whatever stress that you are imposing on this particular cable is one that can be withstand by it. So if it is within what the cable can take, then it will not fail. But if you impose a stress, so what it means is that there's a maximum stress that the cable can take. So as long as you are imposing a stress that is less than that maximum stress that the cable can take, then you don't expect it to fail. Of course, there are other factors that can contribute to failure, but we are focusing now on the one that can result from mechanical loading. So this is one example. So I give a typical example. If you take a child, for instance, mm, if you have like some children in a class, and you have probably 5 of them commit an offense. I think I used to give you this example in class. So if they commit an offense and they need to be punished, for instance, so you see, if you give them same punishment, for instance, their ability to withstand the stress from the punishment vary. So why some of them may cry as a response to whatever kind of punishment you are putting them through, others may be able to withstand it and then they will not cry. So this is the same thing that is happening here. So if you are imposing a load on a material, you must understand the stress resulting from the application of that load, and then you must know what is the maximum stress that that particular material can withstand. So if the stress resulting from the application of the load is less than what the material can take, the maximum load, the maximum stress the material can take, then it means the material can take that load and it will perform the functions that you intend it to perform effectively. So this is another example of a bridge. So in the form of a bridge, you see in this case, it's not a tension. This is to show you a simple example of a simple compression. So example of a simple compression, if you take this particular member of the bridge, this part you can see the cursor, so I bring it out here. So you will see that based on the load that is applied on the bridge, so what the kind of load that is imposed on this member is going to be a compressive load. So that compressive load is also going to impose a stress on this particular member of the bridge, and then you expect that the material that in which you have used for this member should be able to withstand that compressive stress. So you can also measure the compressive stress by knowing what the magnitude of the force is and the initial cross-sectional area of the material. That will allow you to be able to calculate the compressive stress, and then you can know if it is one that can be withstood by the material or not. So for both tension and compression, you can always estimate, which is where we'll focus this lecture on simple tension and compression. In higher lectures, you are going to look at shear stresses, shear strain. You are going to look at torsion. You are going to look at the deformation that results from torsional loading. But for this class, we are going to focus we are going to focus on simple tension and simple compression, and try to understand the mechanical properties that you can derive from the application of a simple tension and compressive load on a material, because it will give certain unique deformation. So we are going to understand the deformation that will result from tension and compression, and the resulting mechanical property that you can have from that kind of application. So in understanding the effect of tension and compressive load on a material, the result is that you are going to have two quantities to understand, which is the engineering stress and engineering strain. So the engineering stress resulting from application of either a tension or a compressive load is force divided by the original cross-sectional area of the material. So for both tension and compressive load, this is the mathematical relation that defines the engineering stress. While the engineering strain is the change in the length by the original length of the material. So what it means is that if you apply a load to a material, the consequence of the applied load is that you are going to have a deformation. Now this deformation will cause a change in the length from L naught to L. So say for instance, look at this diagram you can see here is an example of a simple tensional load on a cylindrical object. So you see the initial length is L naught, and upon application of the load F, you have an elongation to L. So the change in the length is going to be the final length minus the original length. So if you want to calculate the engineering strain, it is the change in this length by the original length that gives you the engineering strain. So what you see now is that the engineering stress will have a unit of Newton per meter square. So Newton per meter square is also known as Pascal, and most material will have a unit that in the range in the magnitude of megapascal or gigapascal. So the strain here has no units because the change in length by the original length has similar units, so they will cancel out. So the difference between tension and compression is just the direction of the force. So for tension, you have an elongation. So what you have is that the final length is greater than the original length. But for compression, you have an opposite of tension. So in this case, what you have is that the final length will be less than the original, and so you have compressed the material. You are reducing the length of the material. So that is what you get with compression. So usually when you measure the strength, you by convention the stress and the strain, you assign a negative sign to indicate that it is under a compressive stress or a compressive strain, and if it is positive, then you know it is in tension. So for shear stress, we are going to look at pure shear stress. So in this case also, you have the same mathematical equation to calculate the pure shear stress. So what you have here is still force by the original area. So the area here is this shaded area, and then the applied force. So you will understand here that the difference between shear and the compressive of the tension is the relationship between the direction of the normal of the surface and the direction of the applied force. So here you see that the surface is parallel, the applied force is parallel to the surface. So once the applied force is parallel to the surface, you will have a shear stress, and then that shear stress is the magnitude of that force divided by the original area. So you also get a stress with a unit of Newton per meter square, which is also known as Pascal, and then this can go in the magnitude of megapascal, gigapascal, and the likes. So now, but here what you have here in terms of deformation is more of an angular deformation. So you see, how do you understand the deformation here is that you see the dotted line indicates the original position or the original state of the material, and then upon application of the load to generate a shear stress, that's the shear load, what you have is a shear of the material. So you have a deformation which will now make the material have the material now have the thick line structure. So what you see is that there's an angular difference between the initial state and the final state. So you see this angle theta that you have here is what defines the deformation that you have with shear loading. So for pure shear strain, the shear strain is going to be a tangent of this particular angle. It is as simple as that. So now when you apply load, so now let's focus now on our simple compression or simple tension. So like I said, once you apply this load, the consequence of the load can be measured by understanding what the stress is. Now, resulting from the application of the load is deformation. Now, this deformation can come in two forms depending on the magnitude of the applied load. So, you can have either an elastic deformation or a plastic deformation. You can have either elastic deformation or plastic deformation. So, the first one is elastic deformation. Now, the elastic deformation is a form of a reversible deformation. It is one in which once you apply the load, the material deforms. Now, if you have a situation whereby upon the removal of that applied load, the material is able to return completely back to its original state, then you will now understand that the load application has caused an elastic deformation. So this is why it is called reversible. It means the material is able to recover completely from the applied load. So once you apply a load and upon withdrawal of that load, the material is able to return completely back to its original state, then in that case, what you have done, the kind of deformation the material has experienced is what is called elastic deformation. Now, you must understand in an engineering application when you need an elastic deformation and when you need a plastic deformation. So if you understand that, so because in some cases you don't want to apply a load that will cause a plastic deformation. You want it to be probably once there is a deformation of the material, it will affect the operation of that material. So you don't want a permanent deformation. You want a deformation that can be reversed. So in that case, you have to understand what the elastic property of that material will be, because that is what will control the deformation of the material that allows it to return or recover completely back to the original state upon withdrawal of the load. So how do you understand this complete withdrawal? If you look at these schematics on this slide, so you have, if you look at this shape, so this is the body, this is the material, this is the initial state of the material. So we carve out a small portion of it and we just illustrate that portion with arrangement of atoms. So you see this is the initial. So once you apply a load F, you are going to have a deformation here, delta. So a deformation as the result, so we kept this part fixed. So we don't expect any movement, any deformation from this point. So we have now applied the load from this particular edge. So if you apply a load from this edge, so what you get is that the material will deform upon application of this load F. It will deform through a length delta. Now, as it deforms through this load, this delta, the implication now is that if you withdraw this load F, and the material is able to return back to the way it was originally, then it means that the material has deformed elastically. So this is what is called elastic deformation. You apply a load, the material deformed through a distance delta. Upon withdrawal of that load, the material returns back to its original state. Then it means the material has undergone an elastic deformation. Now, this elastic deformation can be linear, it can be linear elastic, it can be non-linear elastic, depending on the type of material in question. Now, beyond the linear elastic deformation, you can also have a material go through a plastic deformation. So what happens when you have a plastic deformation is you have a permanent deformation. So you see, this is the difference from elastic. Here you have a permanent deformation. So what it means here is that if you apply a mechanical load to a material and it deforms as a result of that loading, upon withdrawal of the load, if the material is not able to recover completely back to the way it was initially, then it means that the material has been permanently deformed. That kind of deformation is what we call plastic deformation. Now, this plastic deformation means that if you apply the load and the material deforms, when it is going to return, it will not return back to its original state. It will have incurred certain permanent deformation in itself. So therefore, you don't have exactly what you have originally. Now, that deformation is what we call plastic deformation. So using the same schematic to explain it is that you have the atomic arrangement like this initially. So you apply a load. So if you apply a load If you apply only within to have only an elastic deformation, it will return. But if you go beyond elastic deformation, which means that you applied excess load that allows it to deform plastically, so you have both a plastic and elastic deformation. So upon withdrawal of this load, what will happen is that the elastic part that has deformed will be recovered, but the plastic part will not be recovered. So you now have a permanent deformation now. So what you now see is that the length of the final material, even though you have withdrawn the load, will now be higher than that of the initial. So you now have incurred a plastic deformation in the material. So this particular deformation is an offset from the original length of the material. So now, what is the essence of this now? What the essence is that if you understand that a material will deform plastically as a consequence of the load that you are applying, then you must also understand what influence it will have on the operation of the material, or so during application. So if you don't want, if you are using a material for during an engineering application, for instance, and the application is subject to the length of the material. So you see from here, a plastic deformation will cause an increase in length of the material. So if the length will increase, then you don't want the material to deform plastically during operation, so that it will not fail during operation. So this is very important to understand both elastic and plastic deformation of a material. So what we now need to understand next is the effect. What are the effects of this deformation? So the consequential effect of this deformation is to understand what are the mechanical properties that can arise, or that you need to know from this deformation. So how do you now understand these mechanical properties? The only way you can understand this mechanical property is to carry out a stress strain test. Now, the stress strain test will allow you to understand the mechanical properties that are associated with both elastic deformation and plastic deformation. So if you know those mechanical properties, the mechanical properties will now guide you in understanding your load application during operation. So I give you a typical example. So if you say, for instance, if there's a mechanical property that is called say tensile strength, for instance. So tensile strength of a material, you need to know what it is. So if you know the tensile strength, and you are going to be putting the material through a tensile load, and you don't want it to fail, so it means whatever loading you are putting the material through, the resulting tensile strength from that load must be less than the tensile strength of the material. So the moment the applied tensile strength is less than the tensile strength of the material, then the material will function, it will not fail. But once your applied strength is greater than the tensile strength of the material, then the material will fail. So this is the reason why you need to understand what the mechanical properties of the material will be, and then that will allow you determine whether determine your applied properties during application of the material. So in some cases, if you make a design, and then in your design you have already specified the loading condition during operation, so those loading conditions will give rise to certain properties that will be applied on the material. So if the material will not be able to withstand those loading condition, then you may need to change the material, or you need to revise the loading condition. So how do you measure the mechanical properties of a material? Is by carrying out a stress strain test. So usually, the stress strain test is done with a universal mechanical testing machine, and we have one. We have one in the lab. The one we have in the lab, I think, can serve a quite number of material, although it has limitation. I will explain the cause of this limitation as we go along. Now, the um the mechanical property you want to measure means that you have to subject the material through certain loading conditions that the material will be experiencing in real life during application. So, but basically, for the purpose of learning, we're going to look at simple loading in form of tension and compression, and then see how that will allow you measure the compressive stress tensile stress or the tensile strength of the material. So what we do, what is really happening in the mechanical testing machine is that you have simple process that is taking place there. So you have a situation where you are able to control the load. You apply the load in certain direction as you wish, and then you are able to measure the resulting deformation from the application of the load. So how do you do that? The machine has facilities in it that allows you to control the load. So what you have is you have a simple setup as you can have like this. So you prepare your specimen in this dog bone format, and then you have on the machine there is a load cell. The load cell allows you to apply the load controlled. It allows you to control the applied load, and then you have an extensometer that will be attached to the specimen. So the extensometer is able to measure any deformation that is experienced by the material. So you have two things. You have applied load coming from the load cell. You have the deformation measured by the extensometer. So at the end of the day, you can have a relationship between the applied load and the extension. So this relationship between the applied load and the extension can be translated to the stress against the strain. It's as simple as that. How do you get the stress? You get the stress from the applied load, and then you will get the strain from the resulting elongation, which is the deformation. And what allows you to get that deformation is the extensometer that is attached to the specimen. So once you prepare your specimen like this, you mount it on the machine. The machine is able to give you this relationship. So in fact, the modern day mechanical testing machine can plot a graph of the relationship between the applied load and the deformation, which is the extension of the material, or the elongation or the reduction in the length of the material, depending on whether you are applying a tensile load or a compressive load on the material. Now, you see, this relationship that is generated is what you will use to determine or to measure, to calculate all of those mechanical properties, be it within the elastic range or the plastic range. So within the plastic deformation range, this is so if you apply this explanation that I just made on this machine, so you will have a situation whereby there is going to be an initial proportionality between the stress and the strain, after which that proportionality disappears, and then you have a curve, and this will continue. So you have to do this continuously until the material fails. You have to do this continuously. So so this is more of like a destructive test. So you put the specimen on the machine, you apply the load, and then you apply the load continuously, and then you measure the deformation at intervals, and then you do this until the material fails. So this will allow you to know what is the maximum load that the material can take, and then this can allow you to measure all of those maximum properties that are associated with the material. So what in simple statement, if you know what the maximum load the material can take is, then it's very easy for you now to know what the maximum load you'll be imposing on the material will be during operation. So say for instance, if you test a material and the maximum load that fills the material on the machine is, say for instance, 1000 Newton as an example. So during operation, you don't want to come close to 1000 Newton. You don't want to apply a load close to 1000 Newton because you don't want failure. The failure can be very catastrophic, it can cause a lot of destruction, so you don't want it. So this is why the material and its property is very important in any engineering design. So if you look at this diagram now, I have tried to distinguish between elastic and plastic deformation from here. So you see this first part that has this arrow down and up, this faint line is the initial stage, which is elastic, where you can have elastic deformation. So from this 0 up till this point, you have elastic deformation. So what it means is once you load within this region, the material will always return back to its original state. So you have elastic deformation. But the moment you load beyond this point, the material does not return back to 0. The material will return somewhere greater than 0. And that somewhere greater than 0 is what is called the plastic strain. That is the permanent deformation that the material has incurred. So this permanent deformation is very important, and it will assist us in understanding what the plastic property of the material is. So now you see this point where elastic deformation terminates, and above which you will have plastic deformation is what we call the elastic limit of the material. So what it means is that below the elastic limit of the material will experience elastic deformation, and above this limit, the material will experience plastic deformation. So what are the properties that you study with elastic deformation? So here you remember that a non-permanent deformation of a material is what will result in elastic deformation, meaning that upon removal of the load or the stress, the material is able to return. So what you have here is a linear relationship. The consequence of elastic deformation is that there's a linear relationship between the stress and the strain. There's a linear relationship between the stress and the strain, and this is defined by Hooke's law. So the same Hooke's law that you know from your high school, from your O level, is what you have here. So provided you have not exceeded elastic limit, then the stress is proportional to the strain. So you have this equation: stress is proportional to the strain. So if you remove that sign of proportionality, you will get a constant. That constant is what is called E. E here is called modulus of elasticity, or you can also refer to it as Young's modulus. So you have this relationship for elastic deformation of a material, where the strain is proportional to the stress. Now I repeat and I emphasize, this is only applicable within below the elastic limit, where the material has deformed elastically. Now, above the elastic limit, where you have plastic deformation, you are not going to experience this. This will not be the case. So in this case, you will get this relation between the stress and strain. Now, this constant of proportionality here that is called modulus of elasticity is what defines the measure of the resistance of the material to elastic deformation, which is also known as stiffness. So this E is called modulus of elasticity. It is also referred to as Young's modulus, and it is the stiffness of the material. It is measured in Newton per meter square. So it also goes in the range of Pascal, megapascal, gigapascal. So the stiffness of the material, or the modulus of the material, is the resistance of the material to elastic deformation. So the higher the resistance of the material to elastic deformation, the higher the modulus of elasticity of the material, the stiffer the material is. So if a material is very stiff, meaning you find it very difficult to deform, then it's going to have a higher elastic modulus. And then if it is easier to deform, then it will have a low elastic modulus. So if you take, for instance, if you take a plastic material, if you take a polymeric material compared to, say, a ceramic material, you see that the ceramic material, in fact, it's difficult to deform it elastically. So you see it's stiffer than the polymeric material. So you see they will have a higher elastic modulus compared to polymeric material. So this is so the first property that is associated with elastic deformation is modulus of elasticity, and it is defined by stress is equal to elastic modulus multiplied by strain. So the other property associated with elastic property is the Poisson ratio. So quickly here is to understand that if you apply load and there is a deformation on a material, there is going to be elongation in two ways. So if you apply a tensile load to this material, it will elongate along this direction. It will elongate along this direction, but it will contract along this direction. So what you have now is that there is strain in two directions. So what it means is that if you apply load on a material and it is elongating in this direction, then on the transverse direction you will have a contraction. And then if you apply a compressive load on a material to reduce the length of the material, it will elongate in the transverse direction. So what it means is now you have two strain. You have one strain in this direction and you have strain in the transverse direction. So the relationship between these two strains is what defines the Poisson ratio of the material. So this is also an elastic property of a material. So if you take this direction Z and direction X as you have here, so if you apply a force along direction Z. So what will happen is along Z, L naught will become L. So you have an increase in the length, which is L naught plus delta L. But you see this D naught will reduce because of that elongation along that. So along Z, there is elongation. Along the X, there's going to be a reduction in the diameter of this material. So how do you now define the Poisson ratio? The Poisson ratio now is going to be the strain along X divided by the strain along Z. So with a negative sign. So negative EX divided by EZ will define the Poisson ratio. So it is the strain along the vertical divided by the horizontal. So the strain along X divided by the strain along Z will define the Poisson ratio of the material. Now this negative sign is there because you know that one of these strain will carry a negative sign. One of them will carry a negative sign because of the reduction in length, where the final length will be less than the original length. So you have a negative strain. So once you put that negative strain, it will take out this negative and then the strain will be negative. So this is how you measure the Poisson ratio. Okay, so this is in this slide, what you have is a list of class of materials and their respective Poisson ratio. So what you will notice is for metals, you can see the range of their Poisson ratio. For tungsten, for instance, you have 0.26, for nickel 0.29, for copper 0.31. And then if you come down to polymeric material, you see they have a higher Poisson ratio. And then for elastomers, you see you have 0.39. So what all of this is trying to indicate is to have a relationship between the elongation from both axes of the material and how much of elongation you can have. So these are typical values for Poisson ratio. So you see that the Poisson ratio of a material usually will not exceed 0.50. So I will stop the part one at the lecture here for part one, and then I will continue plastic deformation in part two of the lecture. So please watch out for part two, which is also going to be the concluding part of this particular lecture on mechanical properties of engineering materials. So thank you.